I know you've been on tenterhooks. Anyway, we were taking a look at a scenario where we shuffled up a standard poker deck, 52 cards, and we were trying to figure out how likely it is that if I get dealt a single card, that it's either a face card or a diamond. And we're going to approach this a little bit, what you might say, naively. That's okay. You may already see where this is headed, and that's fine if you do. Excellent, actually. So, uh, based on what we've seen before, you might end up doing something like this. So we split this up, probability of a face card plus the probability of a diamond. We've said before there are 12 face cards in the deck. So diamonds, there's 13 of each suit. We've said that as well. And you get to this point. So you might add those up. Again, the denominators match, 25 over 52. And then all of a sudden, light bulb goes off. And you think about, hey, wait, this move requires these events to be mutually exclusive. And yeah, are these mutually exclusive? Can you be dealt a card that's both a face and a diamond at the same time? Yeah, you kind of can, right? So, doggone it. It turns out it's not actually that big a deal to fix in the grand scheme of things. As a matter of fact, the real problem is that we're sort of double counting some cards, right? Because the ones that are both face cards and diamonds are in both sets at once, and so they're getting counted twice. So all we really need to do is subtract out one of the 2 times we counted them to get rid of the double counting. So how many cards live in both sets at the same time? Well, there are 3. The Jack, Queen, and King of Diamonds. So that's the fix. We just, tack on a subtraction of, both, the probability that both occur. So then, again, working my way across, we get to 25. 25 over 52 minus 3 over 52 gives me 22 over 52, or 11 over 26 for a final probability. So as it turns out, I technically, if I didn't feel like starting with the whole mutually exclusive thing, could have just given you that formula in the first place. Probability of A or B is probability of A plus probability of B minus probability of both. And then if they happen to be mutually exclusive, you just kind of cover up that bit because that probability is 0. So that's one example. Let's take a look at one more, and then I want to talk about something a little bit different. So the context here, imagine you're hosting a game night. So you've got, you've invited some, folks over. You've got 12 people that, said they were going to be coming. Of those 12 people, 6 of them are chess fans. 7 like playing checkers, and it says that 4 of the folks we've invited like playing both games. So you're basically trying to figure out how likely it is that when the first person arrives, don't ask me how you know exactly one person is going to get there, just roll with it. That you got to get out that like Pressman, dual, chess checkers set that you've got from like Dollar General or whatever. So in this instance, we want to know how likely it is that the first game we play is either chess or checkers. Again, based on whoever gets there first, and assume it's random, you get the idea. So, are these events mutually exclusive? No, they're not, because I've already told you there were people who liked both games in question. So we have the probability the first person likes chess, plus the probability they like checkers, minus the probability that they're cool with both games. So based on the data we're given, there was a 6 over 12, or if you wanted to reduce it, 1/2 probability that they like chess, 7/12 probability they like checkers, minusing the both, so that's minus, or don't tell anybody I said minus. Oh crap, the internet knows I said minusing. Oh well. So now again we work across 6 plus 7 minus 4. That gives me a 9/12 probability, or if you like to reduce the fraction, as I'm prone to do, 3/4. So, got that one done. I like using this particular example because problems like this are the one case where I find students are most prone to say something that if they stop and consider it, it ends up being ridiculous. So, if you don't remember to subtract away the probability of both in this instance, and that guy's missing, 6 over 12 plus 7 over 12 would give me 13 over 12. And at that point, some alarm bells should start going off because you can't have more than 100% chance that something happens. I wish all of my students would catch that. But every now and again, I have somebody who cheerfully tells me that there's a 112% chance that something happens, and then we get kind of confused. So I want to take a look at one more example of this OR stuff in action, and then change gears and talk about something else. So I'm going to do something, and if you don't get this, it's okay. Okay, so back to this ridiculous kumquat survey that we used in the previous video. Well, I guess a couple of videos ago. Whatever. So we interviewed people, first year student, continuing student, would you rather eat a kumquat, would you rather be poked in the eye? So if you were dealing with an OR situation when you're given data that's sorted as a survey like this, you can actually even get around having to invoke the formula. You can, it's just not necessary. So if we were looking at this and say we wanted to know how likely it was that if we picked out a person at random, they were either okay with eating the kumquat, or they were, in fact, a continuing student. Now, again, technically you could break this up. They're not mutually exclusive. We can see right here we've got people who are in both camps at once. But the cool bit about when you're doing these things with surveys is the following. Well, our kumquat folks, they're right here. The continuing students are running right there. So, yeah, technically you can use the formula and subtract away the people who are in both, but we really don't need to, because those are the three numbers we need. We can just pull out those three directly. You could almost, like erase those little, as I said, those lines between the two segments I circled and call it a day. If you add up all three of those numbers, I got 124. And if you add up everybody in the group for the total sample space size, we'd have 203. And when I worked that out as a decimal, I got 0.611, so a little more than 61% chance that this is, that this ends up happening. And you could play around with this as well. But when you're dealing with sort of empirical survey-driven data, an OR probability isn't quite as exhaustive an effort, because you can, just look at all of the regions you need inside the survey and count up those respective numbers without having to worry about the whole double counting thing. All right, one last technique I want to take a look at. Okay, so boards are erased now. I'm trying to make these jump cuts bearable for myself. All right, the last thing I want to take a look at is kind of an examination of an event and its complement. So let me give myself a little more space. So we have the probability of an event and its complement. Hopefully it makes sense. These guys are mutually exclusive. An event and its complement kind of by definition can't happen at the same time. Like, if I say something like, the probability that I either roll a 6 or I don't roll a 6. Yeah, those can't happen simultaneously, right? So I don't need to worry about that whole probability of both thing. So it's just P of E plus P of E complement. But I've already kind of let the cat out of the bag as to where I was going with this, because what's the likelihood that an event either happens or it doesn't? Yeah, there's a 100% chance that either it happens or it doesn't, right? So in probability terms, that a percentage, that's going to be a probability of 1. So now, if we want to know how likely it is that a particular event doesn't happen, we do a smidgen of algebra. I'm basically just going to subtract this thing over here. So the probability of E complement is 1 minus the probability of E, or if you look at it another way, the probability that the event does not happen is the same thing. So that's another trick. It can come in, to play from time to time. There are actually some, more sophisticated techniques that we get into in Math 107 that really make use of this particular maneuver. But it's something that's there. It comes in handy from time to time. We'll use it a bit going forward. So That's actually section 3.3. So in terms of techniques, there's a bit more that'll come later on in the chapter. The big thing I want to think about, going forward is a lot of what we're doing requires us to count up exactly how many elements an event has. Counting. Yeah, we had to do counting once before, right? So the next section, we go back to some of that counting stuff from chapter 2. So keep on watching.